Okay, Assalamualaikum, morning. How are you? Can you hear me? Hello? Okay, all right. Semua dah makan? Okay. All right. I've started the recording for this session. So yeah, let us get started now. Let me share the screen. Okay. All right. Okay. Hold on. Some students are still coming. All right. Can you please confirm whether you can see the slide now? Can you see the slide now? Okay. All right, Jasmine. Thank you. All right. Thanks. So, so we're gonna continue on to PN junction under bias today. Okay. So before we move on, let us recap a few things on the previous topic, which is PN junction under thermal equilibrium. So let us discuss a little bit on these few questions before we move on. All right. So how do we form a PN junction? So how do we form a PN junction? Simple question, right? Anybody would like to write down? Farah? Farah nama last yang saya nampak ni, so I call Farah then. So Farah, how do we form a PN junction? Alright, Jasmine, joining p-type and n-type semiconductor, right? So we form a p-n junction by joining a p-type and n-type semiconductors, right? So once a p-type and n-type semiconductor is brought into contact, what is going to happen? So what do we have? What will happen if the moment you join p and n semiconductors together? What's the very first thing that will happen? Okay, diffusion. Explain that, Azri. Diffusion. While I'm approving your friend. Okay, diffusion of what? Apa akan jadi? Alright, based on concentration gradient, right? So, so electrons on the in the n-type semiconductor will diffuse into p-type, and holes in p-type will diffuse into n-type. Okay. All right. What else? What else will happen? So you have diffusion, and what's next? Apa lagi akan jadi? So the moment they have diffused, then what happens? Anyone else? What about okay, depletion region created. Depletion region created. All right. Where do we have the depletion region? Do we have it throughout the P and N semiconductors? At the contact area, right? At the metallurgical junction. So by the way, do we have diffusion of holes and electrons from the whole area of semiconductors? No, right? Just at the PN junction, near the metallurgical junction, near the contact region. Okay. So what is depletion region? Number 3, what is depletion region? How do you define depletion region? Region where electric field is formed, right? Region where electric field is formed. Why is it called depletion region in the first place? Kenapa kita panggil dia depletion region in the first place? What is depletion? Because the region is depleted of carriers. Okay, the region is depleted of carriers. So the moment we brought P and N semiconductors into contact, so the carriers near the metallurgical junction will diffuse due to concentration gradient. Then the region near the contact will be depleted, right? The region near the contact will be depleted, and hence it's called depletion region. How do we calculate built-in voltage at the junction? Jadi kita nak calculate is VBI times what? VBI is equal to thermal voltage ln so right? So on and so forth. Okay, you can revisit your previous note and look at the equation. All right, so let's move on to this topic now. So as outlined last time, when discussing about PN junction, we're going to talk about few sections. So the first one, we've discussed about PN junction at thermal equilibrium. So today we're going to talk about PN junction with applied bias, which can be divided into 2 parts, forward bias and reverse bias. And the third one, later on, the moment we finish this, we're going to move on to PN junction under illumination, right? PN junction under illumination. And then we're going to talk about a little bit about applications of PN junction. Right, let's recap what we have learned at thermal equilibrium. So if you see here, uh, the moment you have your thermal equilibrium, we have seen potential barrier is developed at the junction, right? So, and this potential barrier holds the electrons in the n-type and holds the holes in p-type and keep them away from further diffusion, right? So therefore you have the diffusion process stops into the other region, right? um, so the potential barrier then maintains the thermal equilibrium. So as long as you have the potential barrier, if it's not changed, then the thermal equilibrium will be maintained. So this is what we have discussed in our previous lecture. So now let's look at this slide, the second slide. Look at the PN junction connection and look at the band diagram as well. So the top one is the schematic of your PN junction with connection, without bias and with bias. You're going to go through one by one, and the below part is the band diagram of your PN junction during thermal equilibrium on the left, right, on the left. And okay, so this one is at thermal equilibrium, and these two, the center and the right part, is when you apply the bias. Okay, so we can see here, hold on, we can see here. So the left one, the top one, is your thermal equilibrium here. So the moment you have your thermal equilibrium, your PN junction will be stabilized. And you can see the band diagram. We've discussed last time that the moment you have your PN junction stabilized, and then your potential barrier here, the QVBI, is developed, then you have a single Fermi level throughout your PN junction. Okay, so as I told you last time, you should be able to draw the PN junction band diagram. So this part A, is for thermal equilibrium, or we also call it zero bias. Tak ada bias lah, huh? So we discussed this one yesterday, right? Zero bias. Thermal equilibrium or zero bias. So part B is when you apply reverse bias. So reverse bias, part B, as you can see. Right, what is reverse bias? Reverse bias is if you connect your PN junction this way, is given by your connection, is dictated by your connection. So if it's in reverse bias, that means p-type here on the left is connected to negative. This one is negative. If you look at the connection, it's negative, right? Negative. And n-type is connected to positive terminal, right? So p-type is connected to negative terminal, n-type is connected to positive terminal. We know that p-type is positive in nature, right? Positive. Kenapa p-type is positive? Why p-type is positive in nature? Because the whole, right, Ashiza? Yes, because the majority carrier in p-type is whole. So bila you connect your positive here, p-type, with negative, opposite polarity, we're going to have reverse bias, right? So p-type here is positive, connected to negative terminal, therefore you're going to have reverse bias. The same goes to the n-type. N-type is negative because the majority carrier is electrons connected to positive terminal, negative connected to positive, you're going to have reverse bias. Okay, so what is the effect of reverse bias to the band diagram? So you can see down here, apa you nampak in comparison to thermal equilibrium punya band diagram? What do you see? from the band diagram of reverse bias, part B. What do you see? What difference do you see? Shift outward a bit, barrier height. Okay, Hazika, barrier height, all right. So what do you see on barrier height, Hazika? Cuba tengok barrier height on the thermal equilibrium. Thermal equilibrium barrier height is equal to QVBI, right? QVBI for thermal equilibrium. So now let's look at the barrier height for reverse bias. So still equation is still sama, Q, but look at the V now. What happens to the V? V now is equal to built-in potential plus your reverse bias voltage, right? So now instead of QVBI, so we now have to add the voltage. So that will be Q times VBI plus reverse bias voltage. VR is reverse bias voltage. Right? So apa jadi kat barrier height? Makin rendah ke makin tinggi? Makin rendah ke makin tinggi? What do you say? Makin tinggi kan? So kalau you ada tembok depan you makin tinggi, lagi senang panjat ke susah panjat? Susah, right? Okay, kalau tembok lagi tinggi, lagi susah nak panjat. Yes. Susah panjat. So that means the moment you do reverse bias to your PN junction, there will not be any diffusion anyway. So sebab barrier height tu makin tinggi, so it will confirm, it will stop the diffusion and diffusion of holes and electrons. Hole dengan electron tak dapat diffuse, just like equilibrium, but even worse because your built-in potential or your barrier height is even higher in reverse bias. Okay. So kenapa kita dapat higher barrier height? If you look at the connection, you can look at this into some YouTube video. Perhaps I can give you the link later on in eLearn. If you look at the connection, the negative terminal is connected to positive, right? It's connected to hole, and your positive terminal is connected to n-type, which is electron as the majority carrier. Apa jadi bila negative charge and positive charges sit near to each other? Apa akan jadi? This is negative and positive, positive and negative. Will it attract or will it repel? Tarik, right? It will attract. So bila negative terminal is connected to p-type yang ada hole as majority carrier, it will attract the hole to the end of the PN junction, or to the end of the p side, ke arah quasi neutral region, right? It will attract towards quasi neutral region, and the same goes to the n-type. N-type is negative connected to positive, positive and negative attract. So whole electron as the majority carrier in the n-type is attracted towards the end of the connection, ke arah hujung connection tu. So when they are attracted, they are moved away from the depletion region. Dia ditarik ke tepi. Dia tak di-push ke tengah. Dia ditarik ke tepi. Right? So as a result, you also have your barrier height increases and your majority carriers stay away from the depletion region. So bila you do away from depletion region, lagi of course it's a lot harder for you to cross the junction. Okay. So on the other hand, let us look at the forward bias. Okay, C is forward bias. Look at the connection now. So P and N maintain. So alright, I forgot to mention something just now. The moment you add your circuit, your PN junction to reverse bias, do you notice any change to the depletion region? What happens to the depletion region? Apa jadi depletion region in comparison to thermal equilibrium? Cuba tengok. Right? Yeah, it's wider. Exactly, it's wider. Depletion region becomes wider. Okay, in comparison to thermal equilibrium. Okay, good. So conclusionnya, bila you letak reverse bias, opposite polarity, you're going to have wider depletion region and majority carries away from depletion region and very high increases, right? Those are among the essence of reverse bias connection. Okay, jadi kita tengok pula the comparison to forward bias. Okay, now let's look at C, forward bias. So we get forward bias when we connect our p-type, which is positive in nature, sebab hole dia punya majority caloric concentration, to positive terminal, right? Positive terminal. Positive connected to positive becomes forward bias. So negative terminal connected to negative, which is whole electron, sorry. So negative connected to negative becomes forward bias as well. So the conclusion is, if you connect the same terminal to the same polarity, you will get forward bias. If you connect reverse polarity to your opposite carriers, you're going to have forward, reverse bias, right? So now let us look at the band diagram of forward bias. Okay, what do you notice in terms of difference of forward bias band diagram in comparison to thermal equilibrium? Apa jadi sekarang kat dia punya band diagram compared to A? Very high. Okay, Farah, very high. So what happens with very high? Okay, smaller, very high. Yes, good. So bila kita buat forward bias, so whatever you do in the first place, try to compare with the thermal equilibrium condition. Okay, so in thermal equilibrium, you have a very height of Q times VBI, but the moment you have a forward bias, look at the VB, look at the effective voltage there. So Q times VBI minus VA, and VA is the forward bias applied voltage, right? So sekarang dia punya V kena tolak. Tadi kalau reverse bias, V kena tambah. So now Q times VBI minus VA, which means your barrier height will reduce. Mana you punya barrier height? This is TE, thermal equilibrium. This is forward bias, and this is reverse bias. Okay. So the moment you have your barrier height reduce, apa akan jadi? Kalau tembok lagi rendah, senang lompat ke susah lompat? Senang kan? Kalau sebelum ni tembok tinggi kepala, throughout, left to right, throughout. Sekarang tembok tinggi lutut je. Lagi senang kan? Lagi senang. So it's a lot easier. Then that will result in further diffusion of electrons and holes to the opposite side. Just like when they are just brought into contact. Macam mula-mula tadi sebelum dapat thermal equilibrium, right? So we will induce electron flow again from right hand side to left hand side, and we'll also induce hole to flow again, to diffuse again from left hand side to right hand side, right? So this is what happens. You can also notice that there is a change in the Fermi level. Kalau sebelum ni at thermal equilibrium, you're going to have a single Fermi level for p-n junction. If you have reverse bias, you're going to have the Fermi level splitted far away, and if you have your forward bias, you're going to have your Fermi levels on both sides just splitted, just a little bit split, not so much, right? Okay, is it clear so far in terms of what happens to your forward bias or reverse bias, polarity, connection, and the effect to the band diagram? Okay, all right, that's good. So nanti just try to go back and then try to draw the band diagram yourself without looking at the note. Cuba draw a thermal equilibrium condition and then reverse bias condition, forward bias condition, so that you can at least you can feel what is it like drawing with different bias condition. Okay, done. So let us move on to the next slide. So this slide is actually the summary of what we've discussed in the previous slide. Okay, so let's look at the reverse bias. The potential of the N region is positive with respect to the P region, so that the Fermi level in the N region is lower, right? This explains the split of the Fermi level, right? So the potential of the N region is positive at reverse bias, okay? So but opposite polarity, right? So when the potential of the N region is positive with respect to the P region, the Fermi level of the N region is lower than that in the P region, right? So potentially more positive, then the Fermi level is lower. The total potential barrier is now larger than that of the zero bias condition, right? So as we discussed now, so the barrier height is now increased in comparison to the thermal equilibrium conditions, but your voltage is now Q times VBI plus VR, okay, reverse bias voltage. So the increased potential barrier continues, right? The key here is continues to hold back electrons and holes so that there is still essentially no charge flow, hence no current. So sama je macam thermal equilibrium condition, even worse than that because the barrier height is now higher than the thermal equilibrium condition. So there is still no charge flow, no current flow. So that's the summary, more or less, the summary for the for the reverse bias. So now on the other hand, let's look at the forward bias condition. When a positive voltage is applied to the P region with respect to the N region. When a positive voltage is applied to P region, right, this one is the same polarity. So Fermi level in the P region is now lower than that in the N region. Potential barrier is now reduced. So the key is potential barrier is now reduced in comparison to your thermal equilibrium condition. Smaller potential barrier means that the electric field in the depletion region is also reduced. Electric field is also reduced. The smaller field means electrons and holes are no longer held back, right? Held back in the N and P region respectively. Means they can start diffusing again, right? They can start diffusing again. So there'll be a diffusion of holes from P to N across the space charge, and the opposite region is also true. Okay. So okay, I forgot something is now. If you look at the forward bias condition, do you notice what happens to the depletion region width in comparison to this? Smaller, right? Yeah, smaller. I forgot to mention now. So it's now smaller. So if you look at the polarity connection just now, uh, not negative, it's positive actually. Positive is connected to positive. Kalau kita nak explain in terms of the charge, repel and attract. So positive and positive, what happens? Attract or repel? Repel, right? So the positive polarity, positive connection is going to repel holes which are positive and electrons which are negative, negative. Then holes and electrons in the quasi-neutral region will be pushed towards depletion region because of the repulsion mechanism. So they'll be pushed towards the center of the PN junction, hence making the further diffusion of the carriers easier compared to the thermal equilibrium condition. Okay. Forward bias. Right. Again, forward bias. Similarly, there will be a diffusion of electrons from N type to P type. The flow of charge generate a current. Right? Now, due to the flow of the charges now, kita akan dapat current just like the one we discussed during the charge transport. So you're gonna have diffusion. So therefore you should expect diffusion current density across PN junction. Okay. So there'll be injection of holes into N region, means that these holes will be minority carriers. We have discussed 2 days ago, I think. 2 days ago, if you still remember the curve shape like this, x is the distance through PN junction. This one is the carrier density. Let me put it as a density. This one is the depletion region. W. Still remember this curve? And also this one. When we need to calculate the PN naught and NP naught, right? If you revisit your previous topic. So this is what it means by this. The injection of holes into the N-type region means that these holes are now minority carriers. So if this is your P-type, so hole is the majority carrier in P-type. So the moment they now diffuse into the N-type, so now the hole become minority carrier. So you then need to calculate the density of hole by using the PN naught. It's now no longer PN naught actually. It's just PN, but at some point in N type, because naught is only for thermal equilibrium condition. So you then need to calculate PN, which is a factor of exponential reduction of the profile, right? So we're going to see the equation later on. So likewise, the injection of electrons into p-type region, so electrons from n-type into p-type, so electron also become minority carriers in p-type. Dekat sini electron jadi minority as well, minority electron. Okay. Right, this is again the summary of your bias condition. Right, this is a PN junction in forward bias, right? Forward bias, so those are electric field. So this is the connection. Look at the polarity: positive polarity to p-type, a negative polarity to n-type. So therefore you have a forward bias condition. Okay, so that's the VA. This one is the VA, the applied the bias voltage. Then this one is the barrier height. Then the barrier height will actually reduce due to the application of the forward bias. Okay, so that's the depletion region. This is another summary actually. Right, you can summarize all the three band diagrams like this as well. Tadi kita dah tengok satu summary, and this is another way as well. You can put it like this. They are essentially the same anyway. So the first one is the zero bias condition or thermal equilibrium. Okay, the barrier height, notice here, is equal to Q psi naught, or also equal to Q VBI. Sama aja, psi naught is VBI. It's just from different sources. So ada source yang pakai this psi naught, and then other sources uses VBI. Forward bias condition with VA, and then the barrier height will be reduced. QVBI minus VA. So like that, the band diagram. Reverse bias, you can also use VR. Either way is fine. So the barrier height will increase because Q now times VBI plus VR or VA if you like. Okay. So conclusion here is the external voltage that we apply, external voltage that we apply linearly affects the junction energy barrier. Okay. So it means that whatever voltage that you apply is going to change the Q, is going to change the Q times the voltage. If you like, you can say effective voltage. Sama aja. So either it's in forward bias where you have to reduce this, or in reverse bias where you have to increase this. Okay, so it will change the barrier height accordingly. Okay, right. Okay, the electric field across PN junction with an applied bias is given by this equation, right? A negative 2q over permittivity VBI minus applied voltage, and then you key in your NA and D square root. Okay, and then the width of the depletion region is given by this. This Ln LP is actually equal to the Xn and XP last time. Sama. So you can use Xn XP or you can use Ln LP. Same thing. It's referring to the same thing. It's referring to the same region. Okay. You can plug it into this equation. I don't want to go through this. Right. This is the which part of the junction, Ln and LP. So this is the Ln part on the right hand side. Okay, this is the LP on the left hand side. Okay, so we've discussed the shape of this curve last time. The charge, this one is on the right. On the right is on positive charge. This is negative charge. Still can recall which side is p type and which side is n type. What is right hand side? N type or p type? PN junction. Right, n type, right? Kenapa n type, Asrizal? Why is it n type? Yeah, ND, right? So you can see clearly here ND. ND is n type, NA is p type, right? ND is donor, donor is n type. This one is acceptor, acceptor is p type. Very clear. Okay. Okay. Now we will see how the current flows through the device, right? The moment you bias the junction to positive, for example, so we've discussed just now that the current will flow, the charges will flow. So you're going to have diffusion of electrons from n type to p type, diffusion of holes from p type to n type. We now have to determine the density of the carriers on the other side of the junction, where holes become minority carrier in n type and electrons become minority carriers in p type. Holes become minority carriers in n type, electrons become minority carriers in p type. Okay, right? So let's look at this slide. How do the currents flow through the device? Previously, we've calculated the carrier distribution at thermal equilibrium. Okay, so now what happens when a forward bias voltage is applied? So we now know that if you apply your forward bias by connecting positive terminal to p type and negative terminal to n type, so therefore you're going to have a forward bias, then you can play around with the amount, with the magnitude of the VA, which is applied bias voltage, to be able to reduce the barrier height, right? So we can see here in the band diagram that the barrier height is now reduced from QVBI to QVBI minus VA due to the positive bias. Okay, positive bias. So now what happens to the carriers? So now let us look at the right diagram. Okay, so y-axis is the density of carrier across the PN junction, and then x on the x-axis is the distance across the PN junction. Okay, so note that left hand side is p type, right hand side is n type, so therefore the majority carrier in p type is whole, right? Is whole. So notice that the moment you have got your what you call your junction, right? Your junction ready. So the majority carrier still doesn't change. Majority carrier in the p-type still doesn't change. It's still given by what? What's the value equal to? And what? And apa? For p-type? Na or nd? Na, right? So this one is equal to Na. Okay. So in p-type equal to Na. All right. So the moment you reduce the barrier height by applying fault bias, so the hole is going to diffuse from left to right, and this A and B is the width, is the edge of depletion region. Okay, so this W is the depletion region, so A and B is the end of depletion region on both sides, A and B, right? So we want to know now what is the density of holes at the end of the depletion region. Kita nak tahu bila dah hole tu dah diffuse masuk dalam p-type, what is the concentration here, right? So that will be given by P and B, because this one is point A and this one is point B, right? Sebelum ni kita discuss about what? P and not, right? We discussed about P and not before this because we are still discussing about establishing thermal equilibrium. Sekarang kita dah dapat equilibrium, but we apply voltage, so it's no longer under equilibrium condition. So therefore, you cannot use not, right? So you cannot use not condition because no longer TE, thermal equilibrium. So now the density of holes is given by P and B. Right. So can anyone define what is P and B? Last time we've discussed about definition of P and not, N not, P not, P and not. Can somebody write what is P and B? Three things, right? Three items that you have to mention in the definition. What is P and not? P and B, sorry. So in this case, what is P and B? If you have to redefine the notation again. Anyone? What is P? What is N? What is B? So that's how you define. Density of electron or hole? Sorry? Density of electron or hole? P and B. Hole, right? So density of hole in N-type material at point B. So that's how you define P and B. Okay? Hole, right? No problem. Sebelum ni kita define P and not as what? Density of hole in N-type material at thermal equilibrium. Right? Itu dalam condition TE, thermal equilibrium. Sekarang kita dah ada bias. It's no longer thermal equilibrium. So you have to redefine using the same technique. 3 steps. P and B. Density of hole in N-type material at point B. Even though the point B is at the edge of depletion region, is already in N-type material. Okay, this point is already in N-type, so you have to define as P and B. Density of hole in N-type material at point B. Okay, so at this point, hole becomes minority carrier. Holes become minority carriers, right? At this point, mula-mula tadi dia jadi majority carrier because it's in p-type material and then it diffuses into n-type. Now they become minority carriers, right? The same goes to n-type material. If you look at the right hand side, it's given by Nn and it's also equal to N. It's also equal to Nd, right? The moment you apply your bias and then you reduce your barrier height, electrons are going to diffuse from right to left, right? Electrons on the right is majority carriers. Then the moment it goes down this, it crosses the p-n junction, crosses the space charge region. Hole at this point is going to become, electron at this point, sorry, is going to become minority carrier, right? And we want to know the density of electron at NPA. What is NPA? So now let's define NPA. Anyone? Density of electrons in p-type material at point A. Yes, exactly. Good. So NPA is given by density of electrons in p-type material at point A. So remember three steps, three things that you have to include in the definition. Okay, density of electrons in which material at what? At thermal equilibrium, at point A, at point B. So in this case, it's NPA, right? So we now know that electrons are minority carrier at NPA and holes are minority carriers at PNB. Okay. So the junction is forward biased. So we then have to determine the density of NPA and density of PNB. So where's the equation? All right. Okay, let's just finish one or two slides. We'll go through the equation a little bit later, right? So if you review drift and diffusion current across depletion region at thermal equilibrium, we can make useful assumption. This one is at thermal equilibrium. At thermal equilibrium, there is no net flow of carrier. Right, at thermal equilibrium there's no net flow of carrier because the carriers just stop moving, and the reason is that the Fermi level is constant throughout the device and hence there's no driving force for carrier flow. So the moment you see the Fermi level is aligned, that means no carrier flow, there's no net carrier flow, right? So from superposition model we can use this equation to explain, right? So if you're talking about current density related to holes, so that will be given by the drift component of hole plus uh, the diffusion component of hole, because the diffusion component is negative, right? So therefore, the drift is equal to diffusion component for hole, right? Equal magnitude but opposite in direction. So therefore, you don't have any net carrier flow. Right, this is at zero bias, right? This at zero bias, right? J if the total J is actually zero, net J is zero. So we can use this model, drift and diffusion, to be able to calculate the total current density in the depletion region for any applied voltage, right? Okay, I think that's all for today. Do you have any questions? We'll continue on this slide next Monday, right? On how to calculate uh, NPA and PNB using equations. So, right, any question at this point? Is it okay? Is it clear so far? Anybody has questions? So far, no. All right. Okay, that's good. Is it clear so far? All right. So, in summary, before we move on, so what I want you to get from this session is that you should now understand what happens when you apply reverse bias and what happens when you apply forward bias in terms of the circuit connection and in terms of the band diagram, right? And then what what is the implication to the current flow? Okay, so if you can distinguish all the three conditions clearly, you can in fact draw yourself in terms of the polarity, connection, and then the mechanism, and then the impact to the band diagram, barrier height increasing, barrier height reducing, and what happens to the current flow, then I think that should be okay already at this point, right? So in the next lecture, we're going to look at how do we calculate the minority carrier hole in p-type and minority carrier electron in, sorry, minority carrier hole in n-type and minority carrier electrons in p-type after the diffusion process under forward bias conditions. All right, so no question. All right then. Yeah, that's all for today. Thank you very much. And see you again Monday, inshallah. Assalamualaikum. Bye bye.